and greet everybody tonight. Wow, it's been like forever that we've seen you all. I think it's back into the Devonian period. I think the last time we saw you, it seems like. But I've seen a couple of you actually since our last meeting, doing some other things, or you had some questions or whatever. So I got to interact with a couple of you anyway. But welcome aboard. If there's anybody in here that's new tonight, welcome aboard. We are videoing every episode of the Zoom Rock Room. By the way, this is version number 111 tonight. This is our 111th episode of Zoom Rock Room. So it makes me feel old. So we're gonna get started here. Before we get started, though, if you don't know the famous Mel, let's welcome Mel into our Zoom Rock Room tonight.
How's it going?
Yeah, I forgot what you look like. I haven't seen you.
I know, I feel like it's been a really long time.
You know what I did the other day, Mel?
What did you do?
I was having problems remembering why I walked into the kitchen to get something.
Okay.
So I bought memory foam for my shoes, and it works.
I feel like that's a new market.
Maybe you should.
I like it.
I had another guy stop by here since I last saw y'all that was looking for donations for the local community swimming pool at Spring Grove Middle School that actually the community uses. He was looking for donations to the pool, and I kept saying no, and he just got really, really insistent that I need to contribute something. So I finally gave him a glass of water. He went away, but
donation.
Yeah, donation. And the other night I dreamt I was a 45 record. I woke up the next morning feeling really groovy. Anyway, let's stop this nonsense. Okay, we have a big intro.
You're getting a couple head shakes. I see them all.
Yeah, good. That means everybody can hear me, or at least don't turn me off. Put it that way, right? Yeah. I just have to remember how to do this. Okay, here we go.
Just remember to share the sound when you play my Dirtman report, sir.
Yep, I got her. Oh. Yep, so 111th version of the Zoom Rock Room started back in April of 2020, actually, and of course you met our co-host Mel, and we want to, of course, always thank, as we always do, Lair Architect out in Lake Havasu City for their backing of the Zoom Rock Room, making all this possible without us charging you anything to come in here and have a little fun, get a little education, a couple times a month. Dirtman's reports, which is upcoming here in a couple of seconds, but tune in to Dirtman Andrew's reports, extremecody.com, and Andrew in his busy work has found time to put one together for you all tonight. So we'll let you enjoy this.
Warning: Penn, Maryland Materials Quarry is no trespassing and only accessible through local clubs like the Central PA Rockin Mineral Club.
Dirtman here with another special report. Today, I'm at one of my top 3 favorite quarries, the massive Serpentine Pit at H&K's Penn, Maryland Materials Quarry. And you know what? We are smack dab in the border of Maryland and Pennsylvania, so today we're going to be collecting minerals in 2 different states at the same time. About 2 miles away, the famous Wood Chromite Mine, the world's largest chromite mining site, while owned by Isaac Tyson Jr., was a 500-foot shaft. That started at about 250 feet of elevation. This mine starts at over 450 feet, so we have to descend quite far into this pit to be able to collect. According to the PAG-33, in the early Paleozoic era, low silica magma solidifies as dunite. Then, surface chemical alteration transforms it into serpentinite. Then, it is intruded by a high silica, hot hydrothermal solution, which chemically reacts with the serpentinite to form most of the minerals we're here to find today. So already I'm finding some really cool stuff. This botryoidal formation here is actually, I think, hydromagnesite. Really pretty cool formation in there. That's a nice, really cool piece of translucent druzy. You can kind of see through it. There's this nice blue over here. Look at that. We're gonna keep looking here, everybody. I'm here with Ken. I gotta go quick here because this rock is heavy. Look at that. Very cool find, Ken. That is absolutely amazing.
Andrew found.
Oh, look at that. Andrew, great job over there finding that. Here with Renee. Of course, she's finding the good stuff. Look at that, everybody. That is some sparkly druzy. Very cool, very cool. Great job, Renee, as always. So many awesome things in this quarry. We are on the middle level now. It's a beautiful day, not too hot. Keep on looking. Look at that, everybody. Andrew just found this really cool internal structures crystalline and kind of separated on the inside. It's sparkling in there. Almost like a concretion.
Yeah, we'll see.
Good job, Andrew. Take a look. This quarry is well known for its picrolite, antigerite, and chromite, as well as its UV reactive minerals. But for this rockhound, what sets this quarry apart from all the rest is the abundance of colors everywhere you look. It's been a great day here at the H&K Penn Maryland Materials Quarry. To learn more about serpentine and chromite, check out my Dirtman report on Isaac Tyson Jr., available on YouTube, along with all my other Dirtman reports from up and down the East Coast. Dirtman here, bringing the geology to you. Back to you, Jerry. Thanks for ruining it. I finally got it right. Ah! Dirtman here, bringing the geology to you. From here at the massive serpentine pit at the H&K Quarry, back to you, Jerry.
Hey, Dirtman!
Warning.
Oh, what a good one. Yep.
That was great.
Yeah, that was well put together there, Andrew. Thank you very much.
Thank you.
Yep. And coming Zoom Rock Room schedule, of course, tonight, Steve Lindburg is going to talk to us about the America's, some of the selected America's national parks. Next time I'll be doing the geology of the York County Heritage Rail Trail. October 3rd, we are going to do a kind of an off-the-cuff program, not totally geology related, but why do we do what we love to do? And October 24th, now notice the change. We're not going to meet the third Tuesday of October. It's going to be the last two. It's going to be the fourth Tuesday of October because of some other arrangements. But Diana Geis, who's in our room tonight, is going to do notes on the Glacier National Park and other points in the West. And that should be rather exciting. And then November, we still don't have definite dates yet. We have some people thinking about some topics that fossil related and also mineral related. And so we hope to fill those in shortly, and actually to get into December and head toward our famous Christmas trivia game later in December. So anyway, mark down October 24th. Will be the second one in October, not what would be October 17th. Okay, I want a couple of announcements here. The 57th annual Central Pennsylvania Rockin Mineral, Gem, Mineral, and Jewelry shows coming up in a few weeks at the Harrisburg Consistory Building, 2701 North 3rd Street in Harrisburg. And of course, we do have some members of the Zoom Rock Room who are members of the club. And it's a fabulous show. And it's open 10 to 6 on Saturday, the 23rd of September, Sunday the 24th, they're open from 10 a.m. to 4 p.m. And lots of dealers, exhibits. JGS will be there to do some programs both days, including panning for gold at one occasion on each day. So put that in your calendar. It's a fun show to come to. Also, maybe Steve Lindburg can say more about this, but Rockin in the Alleghenies is going to be scheduled on October 11th at the Pitt Johnstown campus for the Friends of Mineralogy Pennsylvania chapter. And a lot's going to be going on out there, along with a field trip going on Sunday to the New Paris Quarry, where we had a Zoom rock room gathering a year or so ago. So anyway, if you're into minerals and you want to become a member with the Friends of Mineralogy Pennsylvania chapter, check them out too. This Saturday, if you want to do some geology stuff with me, 9 o'clock in the morning, I'll be at the Millersville Municipal Building talking to the Historical Society about your backyard geology of the Millersville area and anything else I want to throw in there. I'll be at 9 o'clock. And at 1 o'clock, we're going to do a geology walk beginning at what's called the Furnace Road parking lot north of Chickies Rock. And we're going to be walking south on the trail past Chickies Rock and toward Columbia to get to another furnace remain and just see how energetic the group is, how far south we do go in the time. But it is scheduled for a 2-hour time slot. So that will be on Saturday at 1 o'clock. Talk about Chickies Rock and other things right in that area. And both of those programs are free to attend. So come on out, get some exercise in the afternoon, and hear about your backyard geology from Millersville in the morning. As we promised, when we came back together tonight, we want to hear anybody's comments if they went out to see the Perseid meteor shower. That was August the 13th, the peak in the morning. So I would ask you if you want to share anything right now, unmute yourself and give us your report. If you heard, if you saw anything flying through the air. All right. Hearing nothing there.
I've observed the Perseids several times, Jerry.
Okay.
We used to travel from Iowa, where my wife is from, and we drive by car. So we'd leave out there early in the morning, about 4 o'clock. So we were usually out there during the Perseids. So as we were leaving, you'd see all these fireballs just shooting through the sky. They're really spectacular. Quite a show.
Cool. I think some of our areas around here had crappy weather for that morning, if I remember right. There were some areas that were somewhat clear and some areas that were totally cloudy, as usual for any astronomical event. So that's for maybe why we're not hearing a lot of comebacks here. But there was another event that happened just a couple days ago that you might have been reading about this one. And we actually have a on-site reporter with us tonight who I asked to actually tell you about this because he actually put this diagram together thanks to our observer in southern York County. So Ken Frazier, you want to tell us about what you saw?
Yeah, we were sitting out on the patio, and Mary is actually the one that saw this, and Mary hardly ever sees anything going across. And we saw it just from when it got over 83, essentially going north because of a tree that we have blocked. But it was impressive. I mean, it cast shadows on the ground, and it was really neat. About 2 minutes later, we heard either the explosion of it breaking up or the sonic boom, or both as it went across. I did look up more after I made this slide, and they said it weighed probably 60 pounds, and it went off with the explosion equivalent of 1 ton of TNT, which is pretty sizable. What's kind of interesting is if this was going in the other direction and blew up over DC, it actually could have started some alarms going off because they watch for, hypersonic weapons coming in from the north. So it's very good that it went from the southeast to the northwest, but very cool.
All right. You did see that it was traveling 36,000 miles per hour. 44,000 feet. It entered our atmosphere over Forest Hill, Maryland, down there, and exploded into a bullseye 24,000 feet up over Natstown, Pennsylvania. Now, nobody knows where Natstown, Pennsylvania is. It is in York County, just north and a little bit east of Hanover, within the Pigeon Hills.
And those are miles, not feet. It blew up 22 miles up.
Okay, right. Okay.
So I would think that if there was any debris you could find because of the velocity and the height, it probably would have rained down like in the Carlisle area. I don't think it would come straight down into Pigeon Hills, but I'm sure something made it to the ground from this.
I'd have to keep tuned, but that was I saw it was visible from Florida to Miami, Florida to New York State. So if you were outside at 9:30, you saw a good show. All right. Thank you, Ken. All right. And I'm going to pass it over. Mel came up with this little clever game for you to play. It's very, very easy.
Yes. So as you scroll on the internet sometimes when you have a little bit of downtime, I came across this neat little game. It's what's your gemstone name? It's really, easy. There's only 4 steps. I will share my results in the chat. So if everyone wants, or anyone who wants to try it, it's the first 3 letters of your first name, the second letter of your birth month. You have to add the last 3 letters of your mother's first name, and then ITE to the end. You can type it in the chat and send it in. Some of them might be really hard to pronounce. Some might be a little silly. Some might be really cool. You never know. I just, when I saw it online, I obviously instantly thought of the Zoom room and what a fun little introductory game to the evening this could be. So, like I said, if anyone wants to try it and type it in the chat, it could be kind of fun. Like I said, mine is a little hard to pronounce, and some are a little silly. So it all depends on the information according to those steps. But
there we go. A couple. The night micro.
Now it's a little fun, little goofy. Makes the evening a little bit more laid back, a little bit more fun. And something that maybe you could share to kids, to grandkids, to neighbors, family members. And when they ask you, well, what did you do on Tuesday night besides listening to an amazing presentation, which I'm really looking forward to, Steve, by the way, the topic I love. But like I said, something a little fun and lighthearted to share. Durban, I love it, Andrew. I love it.
Very cool.
And then once everyone's kind of try that little icebreaker, whenever Jerry wants to transition into our great presentation this evening, he may.
All right. Just have a couple more coming in yet. It's hard to pronounce, like you said.
Yeah, some are a little funny to try to pronounce correctly.
we should make them do now is for next time they should write down the characteristics of their gemstone,
Yes.
and we
Yeah.
can have
It's a paper. What would it look like?
a new mineral name for each one. Okay. All right. Well, I'm going to stop sharing here. If you still want to bring them into the chat room, you may do that for sure. Okay. Before I introduce quit over to Steve, we had a long weekend this weekend. We ventured into Salisbury, North Carolina last Wednesday, and that's where I went to school at Catawba College, and I got to revisit the campus again. No, I did not have any money for the president of the school like they were hoping to, but saw the campus. I saw some of the new buildings since I've been there, sort of deal. And while we were waiting in Salisbury, we were scheduled to go to Pawleys Island, South Carolina, on Thursday for the long weekend, and we did get the go ahead on Thursday morning from our friends at Pawleys Island that all things were clear with the hurricane and come on ahead. So we went to Pawleys on Thursday, then came back up to Salisbury on Sunday night, and came home yesterday. Pawleys Island did not sustain any damage with the hurricane, actually. We did travel 2 roads getting there that had signs of caution water on the road. One of those that was dried up, and the other one had a very little bit of water on the road yet that we were able to drive through. So thank goodness for Myrtle Beach, Pawleys Island area. They survived this hurricane. Actually, by that time, it was a tropical storm. So we had a big travel day yesterday. Don't ever drive Interstate 81 on a holiday like Labor Day. Not only are there trucks everywhere, there's, of course, everybody going home. So it was bumper to bumper, 2 lanes, traffic, and it was mentally a hard drive to get back to Spring Grove. So anyway, all right. As I told you earlier, our program tonight, and we thank him for stepping up and volunteering this program, something I think he was teaching within the OLLI courses. And we all know Stephen Lindburg very well. He's a participant in the Zoom Rock Room when he can be here. He is a member of the faculty of the University of Pitt Johnstown Energy and Earth Resources Department, where he does teach courses, including, I know, field geology field mapping is one of his favorites, but he has a big interest in ancient history, meteorology. He's a good structural geologist also, and he's a good consultant if you use the app PA Rockhounders. You see him in there quite a bit, consulting other people's questions about what do they have. So with that, Steve Lindberg's going to do us a program on geology of selected national parks. And it's all yours, Steve. Thank you again.
Thank you, Jerry. So got to live up to that introduction. So let me see here. I'm just going to go back to, I just want to go back to this real quick and put in a plug. And also Andrew Rockhound's on the board of directors for the Friends of Mineralogy. At least I believe he is Friends of Mineralogy Pennsylvania chapter. So on November 10th, 11th, and 12th, this coming November, we are hosting the Friends of Mineralogy Pennsylvania chapter symposium, meeting, and field trip at the University of Pittsburgh at Johnstown. People will start arriving on Friday evening. We have like a little social gathering on Friday evening. We're going to open up the basement of the geology department in Krebs Hall. We're currently cleaning out all our extra and spare specimens, minerals, fossils, igneous, metamorphic, and sedimentary rocks. And we're going to have a room filled with those. And it's bring a bucket or boxes, and whatever you can pick up and carry, you can take. So we're going to have a take away our extra rocks evening. We'll either do that, probably do it Friday night or maybe Saturday night. But then on Saturday, we have symposiums with guest speakers, and we're also having a mineral show. And we already have 4 or 5 mineral dealers lined up. They're going to set up, and we're going to have a regular mineral show. It's going to take place at the big Living and Learning Conference Center on campus. Lunch is available. The registration, I believe, if you're a member of the Friends of Mineralogy, registration for the whole weekend is only $10. And if you're a non-member, it's $15. So it runs all day Saturday, and then we'll have a gathering and a get-together Saturday evening. And then Sunday morning, we leave campus and we have a field trip for all registered participants that goes to the New Paris limestone quarry down near Bedford, which is about a half hour from campus. And the New Paris quarry is now privately owned. We have full access to it. I know some of you have been there before. Lots and lots of fossils, calcite. We now have strontianite there. Fluorite, at one time it was famous for its purple fluorite, which can still be found there. We actually have students doing research on that. And we may present that at the symposium. So think about coming out for the Friends of Mineralogy symposium at Pitt Johnstown that weekend. I think we're planning a really, really ambitious program. Bill Stevens, a lot of you might know Bill Stevens. He's currently the president of the Pennsylvania chapter. So we're hoping to attract a lot of people. All right. So anyway, thank you for having me this evening. I'm going to talk about the geology of some of selected America's national parks. And once again, I'm with the University of Pittsburgh at Johnstown. I teach a variety of courses there. Our new semester has just started up. This semester, I'm teaching prehistoric life and geodynamics. And we also offer this as a course. We actually have a 3-credit course that runs the full semester on the geology of national parks. And there's a textbook that goes along with this also. So I'm going to try to go through this pretty quickly. Forgive me if I make a little error or mistake, write that down, make a note of it so we can come back and discuss that. But let's get right into it. The United States has 63 official national parks, and included within the national park system, and we'll talk about Yellowstone, the very first national park, but included within the national park system are also 131 national monuments, which have a slightly different designation than the national parks. Although we won't talk about it tonight, the newest national park that brought the number to 63 is now, and I'm having a senior moment here. It's the Gorge in West Virginia. Jerry, chime in. Give me it's
New River Gorge.
New River Gorge. That's it. The New River Gorge was signed in as the newest national park by President Trump, I believe, back in 2020. And that national park stretches the length of the New River and includes the bridge. I'm not including that tonight, though. So let's talk about what makes a specific tract of land a national park. And by the way, this is actually part of an OLLI course that I teach, and it's also, I've condensed this down quite a bit. We're not going to talk about all 63 national parks tonight. Jerry, maybe we can do a part 2. If you have an open evening in November or December, we can do National Parks Part 2. So what happens in order for a region of the states to become a national park? To be designated as a true national park, a national park must be designated as such by an act of Congress. They are operated by the National Park Service, which is an agency of the Department of the Interior. So if you want to be a national park, it has to be approved by an act of Congress, and then it becomes a law. The size of national parks vary greatly, but all 63 national parks are considered equal in the eyes of the National Park Service. They are considered equal in terms of their mission to preserve the geology, the biology, the ecology, the natural surroundings for use by the American and the international public. Hunting and extractive activities like rock and mineral collecting, firewood collecting are strictly prohibited. There's lots of other subcategories within the national park system. There's national military parks, of which Gettysburg is one. Gettysburg is a national military park, so it has a slightly different designation. It's not included as one of the 63 national parks. So we have 63 official national parks. We have 131 national monuments. So what makes a national monument different from a national park? Congress must act by law to make it a national park, but the President of the United States has the power to declare a region of land or an area a national monument. So the President can simply make a decree and sign it in as a national monument. And Devil's Tower in Wyoming is an example of a national monument, and I believe it was the first. Yes, it was the first national monument. This is covered by the Antiquities Act of 1906, which gave the President of the United States the power to designate a national monument. And what we find is a lot of the 63 national parks that currently exist in the states started as national monuments, and then on a recommendation to Congress, they were voted into law at becoming a national park. And there's a slightly different designation in terms of the governing powers and the rules for camping and ownership of the national park system. So Devil's Tower was designated as the first national monument on September 24th, 1906 by Theodore Roosevelt. So that's the difference between a national park and a national monument. So let's talk about the first national park, which was signed into law. I have to move my little heading here. The first national park in the United States was signed into law by President Ulysses S. Grant in 1872. And of course, that is Yellowstone National Park. And here's a copy from the congressional records that actually made it a national park, be it enacted by the Senate and the House of Representatives, so on and so forth, approved on March 1st, 1872. So here's one of the original, this is called the Roosevelt Arch, the entrance that was completed, one of the entrances to Yellowstone Park. This arch was completed in 1903. Here's a vintage poster from 1938 of Yellowstone Park. And let me see where we are here. So I think everyone is familiar with Yellowstone Park. It's one of the most visited national parks in the United States. The park itself covers an area of almost 3,500 square miles. Yellowstone Lake is one of the highest freshwater elevation lakes in North America. And we'll start to talk a little bit about the geology. Yellowstone Lake and the park is centered over what is known as the Yellowstone caldera. And a caldera is the large collapsed crater over a volcanic complex or over a single volcano. So Yellowstone Park itself in Wyoming and partly into Idaho and Montana is centered over an enormous volcanic caldera. The caldera itself measures 43 by 28 miles. Yellowstone Park is often referred to as a there's a double A in there. I'll have to correct that. Yellowstone Park and the caldera is often referred to as a super volcano. I can tell you that as geologists, we really don't like that term, super volcano. It kind of gives you the impression that the entire state erupts or the entire country is destroyed by the volcanic eruption. And you can get some incredibly large volcanic eruptions from tectonic hotspots and volcanic calderas, but I don't know, we tend to stay away from the super volcano eruption. There is no doubt that in the geologic past, Yellowstone Park had some enormously large eruptions. So what makes Yellowstone Park unique? We know that in the concept, no longer a theory, but we know in plate tectonics that the continents move. There are divergent boundaries where plates spread apart. There are convergent boundaries where plates come together. There are transform boundaries where plates slide against each other like the San Andreas Fault and the offsets on the Mid-Atlantic Ridge. And then there are tectonic hotspots, of which there are numerous hotspots where we have plumes of magma that are rising up through the Earth's mantle. Hawaii is a tectonic hotspot. Iceland is a tectonic hotspot. The Galapagos Islands are a tectonic hotspot, and Yellowstone. The Yellowstone caldera sits over a plume of magma rising through the mantle. And as the overriding North American plate moves, and the hotspot tends to move a little bit too, as the tectonic plate moves over the hotspot, you get a series of caldera or volcanic complexes. This is very similar to the Hawaiian Islands. The only difference is the Hawaiian Islands are out in the middle of a oceanic thin basaltic crustal plate, and the Yellowstone tectonic hotspot is located beneath a continent. And we can actually trace the movement of the Yellowstone plume, the Yellowstone tectonic hotspot, beginning in the southwest. There is the McDermott caldera that dates between 16 and 15 million years old. And then we have the Humboldt caldera, the Bruno Yarbridge caldera. So there are a whole series of volcanic calderas that mark the passage of the North American plate over this plume of magma rising through the mantle. And as the North American plate moves roughly to the west-northwest and has changed direction slightly, we see a series of volcanic calderas, and we can very accurately measure the lavas and the rhyolites and the volcanic eruptions in these calderas. The hotspot is currently located below the northwest corner of Wyoming and the northeast corner of Idaho, and that is the Yellowstone caldera. So the two maps here, we can see this series of volcanic eruptions that have formed as the North American plate moves across that hotspot. So a cross section through Yellowstone, it's a very, very generalized cross section. We have a rising plume from the upper mantle of hot material. It causes the crust to bulge upwards and fracture, and you get volcanic activity, intermittent volcanic activity on the order of every 10, 20, 30, 40, 50,000 years. The caldera itself right now is in a stage of quiet reserve. Groundwater that soaks down through the rocks in Yellowstone, come in contact with the superheated rocks down below, and that results in the geysers and hot springs, but by no means is the Yellowstone caldera extinct. It's very, very difficult to predict when the next volcanic eruption will take place. You can do that with some degree of certainty because we can detect there's a difference between tectonic earthquakes that occur along a plate boundary and magmatic earthquakes that indicate the rising of magma through the crust of the earth. And the prime example of that is last year, the year before, the second volcano, Mauna Loa, became active on Hawaii. And they kind of knew that was going to happen because we detected the magma rising through the Pacific plate under that second volcano, which is north of Kilauea. So lots and lots of geologic features in Yellowstone. Yellowstone Park is famous for the columnar jointed basalt, which forms as the basalt lava flows cool and contract and form these polygonal columns that then crumble apart. We find these scattered throughout the world in volcanic regions. When we went to Iceland back in 2016 with the Geology Club, my department chair was set on bringing back a piece of columnar basalt with him, and he did that. He actually purchased another suitcase and picked up a large piece of columnar basalt and loaded that in the plane on the trip home as a checked bag. So we have a piece of Icelandic columnar basalt. The Yellowstone caldera itself has formed over the last 2.1 million years. This is the Steamboat Geyser. There's a lot of volcanic activity associated with a mass of superheated rock below the surface. The most recent, the last large eruption was dated at about 640,000 years ago. So that would have been a large, once again, I hate to use super volcano, but this was a large, massive volcanic eruption that blanketed the West and the central states with a thick layer of volcanic ash. The most recent lava flows in Yellowstone Park date to about 70,000 years ago. So we're kind of due when we look at the range, the quiet periods in the Yellowstone caldera compared to when we graph all of the volcanic eruptions. We're due. It could happen next year, 10 years from now, 100 years from now, 1,000 years from now. But we're due for the next volcanic eruption. So that is Yellowstone. Let's move on to our next national park, the Petrified Forest in Arizona. I was there a number of years ago. Probably I think one of the more spectacular national parks. The Petrified Forest began as a national monument in 1906. It then became a national park by act of Congress fairly recently in 1962. And when I was researching this was something that I wasn't aware of. I always thought the Petrified Forest was a national park much earlier in the history. So where is that located? It's kind of in eastern north central Arizona. It can be accessed by Route 40 or Route 180. There is a north entrance and a south entrance to the Petrified Forest. You take the large drive, and all through this region of the park, which covers about 346 square miles, you just see endless petrified, permineralized, fossilized trees. We believe most of these trees were carried into this region from a distance by floodwaters. And I was looking for the geologic report. They came in from the east on rivers and streams and were deposited in a massive sandbar. And over geologic time, as the wood decomposed, it was replaced molecule by molecule by different varieties of quartz. Jasper, chalcedonies, multicolored by the chemical elements in the groundwater. This is true petrified wood. It is permineralized, which we often find happening to dinosaur bones. I always have a very vigorous debate with people here in the western part of the state that claim they found petrified wood. Here up on the plateau, we have casts of lepidodendron and sigillaria trees, but true petrified wood, where the cellular structure of the wood has been replaced molecule by molecule by quartz. You really don't find that here. It is present, but it's extremely rare. So the Petrified Forest is famous for literally millions of tons of these giant petrified logs. The Petrified Forest, like all national parks, these pieces of petrified wood are protected. Of all the national parks in the United States, the Petrified Forest has the biggest problem with theft and pilfering of the petrified wood. And the Park Service estimates that every year, several tons of wood are taken out of the park, either with small little hand-sized pieces or larger pieces that people, this is a very, very remote area, and you can drive through the Petrified Forest and not come across a park ranger or another person. You can park your car and hike for miles. And it's very easy to take petrified wood out of that area. It's become a big problem. Let's go back to the Triassic period. So on the geologic timescale of the Earth, the Triassic period is from about 252 million years, right after the Great Permian extinction, to 200 million years ago. What's happening during the Triassic period? Here is what that region of Arizona looked like. We've got the first true dinosaurs evolving. Arizona during the Triassic period was humid to subtropical. We get the rapid evolution of modern type trees, especially conifers. And these are believed to be most of the trees in the Petrified Forest. This area was swampy. We get the mammal-like reptiles that also existed during this time. The first true dinosaurs like Coelophysis are evolving. And this is the Chinle Formation. It is a very, very thick layer of sandstone that's common in the western states. Here's the paleogeographic map of Laurasia, the North American continent, South America, Africa. So we're kind of, we're at the beginning of the breakup of Pangea, which came together during the Permian. So you can see the continents are just beginning to split. And here's the location of the southwestern United States back during the Triassic period. So the trees themselves in the Petrified Forest are truly petrified through the process known as permineralization. On my PowerPoint, it doesn't recognize the spelling of that, but that's the correct spelling. The trees were carried by flowing water deposited in quartz sandstone. And as the trees decayed away, the cellular structure, and this is a magnified view of the trees, was replaced molecule by molecule by the quartz. And you get these beautiful colored bands. Not only does the Petrified Forest contain these beautiful petrified trees, but it's also a prime site for paleontologists to discover the first true dinosaur fossils. And dinosaurs were evolving very rapidly during the Triassic period. It's during the Triassic that we find the first theropods, the two-legged predatory carnivorous meat-eating dinosaurs. And probably the most famous theropod of the Triassic period is Coelophysis. Coelo, which means hollow-boned. And Coelophysis was originally the type specimen by which all dinosaurs were compared to. A lot of famous specimens have been found at the Ghost Ranch in New Mexico, one of the more famous locations for Coelophysis. So that's the Petrified Forest. Let's move on to Crater Lake National Park in Oregon. I'm going to try not to steal the thunder here because I saw Crater Lake is coming up in another presentation. So I'll go through this pretty quickly. Crater Lake became a national park in 1902. The lake averages 6 miles in diameter and covers 20 square miles. Here's a beautiful example in geology of a caldera. This was an enormous volcano and still is extinct, but this is a volcanic mountain in the Cascade, the Pacific Northwest range of the Cascades. The park covers 183,224 acres. This is the collapsed crater, the collapsed cone of a giant coastal subduction zone rhyolitic andesitic volcano. There was a massive eruption here, which I think we're coming up to in a couple of other slides. The volcano then continued to have a rebirth. A smaller volcanic cone formed in the remnants of this massive caldera. This is called Wizard Island. The lake that now fills this volcanic caldera is some of the clearest and purest water that we find on the North American continent. Crater Lake is part of the Cascades mountain range, which includes Mount Rainier and Mount St. Helens. Here is Mount Rainier. And here is, let me see, here's Mount Shasta, and there's Crater Lake, Mount Hood, Mount Adams, Mount Baker. Here is Mount St. Helens. The Cascade mountain range are volcanic mountains that extend through the Pacific Northwest that are a result of there we go. They are a result of the Juan de Fuca subplate that is spreading and being subducted under the Pacific Northwest of the North American continent. And when you take an oceanic plate and subduct it under a continent, the chain of continental volcanoes that you get tend to be higher in silica content. You do find basaltic lavas, but Mount St. Helens, Mount Shasta, the Crater Lake, which was Mount Mazama, continental subduction zone volcanoes tend to have a higher than average silica content in their lava. They tend to be rhyolitic and andesitic lavas, andesite named after the Andes Mountains in South America, and that makes the volcanoes extremely explosive. There's different types of lava. We go from a basaltic lava to an andesitic and a dacitic and a rhyolitic lava. And the difference in those lavas is the silica content. The more silica that you add to a volcano, the stickier and more explosive the volcano becomes. So a volcano like Hawaii is a basaltic lava, and the Hawaiian volcano tends to have very quiet eruptions and the lava flows across the surface. But we go to the Pacific Northwest and the Andes Mountains, and we get these massive, typical cone-shaped volcanoes like Mount St. Helens that are extremely explosive. Crater Lake formed about 7,700 years ago after a huge eruption by Mount Mazama. The magma chamber emptied out, and the volcano collapsed in on itself, forming the caldera. Then there was a second stage of volcanic activity that formed Wizard Island. Wizard Island then emptied the rest of the magma chamber, and since then the volcano has now become a caldera, a lake that is filled with caldera. So here's kind of a sequence in the eruption of Mount Mazama. The Cascade volcanoes, Mount St. Helens is still active. They're simply at a quiet period right now. I can tell you, if you ever go to Seattle on a clear day, and we were in Seattle as a stopover on our Hawaii trip a few years ago. You stop in Seattle, and on a clear day, you look to the east, and Mount Rainier dominates the skyline. It is just such an impressive sight. The entire horizon is filled with Mount Rainier from Seattle. So here are the types of lavas. Little more in-depth geology here. Lava that comes up, magma that comes up through a volcano can vary in its amount of silica. The lowest amount of silica produces a lava that is basaltic. And then as you increase the amount of silica, which is picked up as the magma flows up through the continent, the lava becomes andesitic, and then it becomes rhyolitic. And rhyolitic lavas are the most explosive, viscous, gas-filled, and destructive types of volcanoes that you can have. And these tend to be the continental plate tectonic volcanoes. So let's leave Crater Lake behind, and we've got to talk about the most visited national park in the United States. Once again, I'm kind of going a little fast here because I've got more national parks to do. So Great Smoky Mountains National Park. President Calvin Coolidge signed the bill in 1926, establishing Great Smoky Mountain National Park and Shenandoah National Park, which is a separate national park. This is an enormous tract of land, and it took an enormous amount of money to make improvements in the park that were mainly done by the Civilian Conservation Corps, the CCC. From 1927 to 1928, funds were raised to purchase tracts of land to add to the original park that was signed into law. In 1931, Tennessee and North Carolina added an extra 300,000 acres of land. They deeded it to the government. Development of the park began in 1933. And for the first time in 1941, the total number of annual visitors reached 1 million. So today, Great Smoky National Park is the most visited national park in the United States. I don't have the figures for like 2022. Of course, during the COVID era, those numbers went down, but the amount of visitors far exceeds 1 million people per year. And I think the reason for that is where it's located. You're on the East Coast of the United States. You have spectacular mountains, hiking trails, camping, awesome geology, lots of wildlife, bears everywhere. So if you want to see bears, you go to Great Smoky National Park. And I know one of Jerry's favorite places might be Cades Cove. You take the drive through Cades Cove before you cross over the park and go down into Gatlinburg. And you're guaranteed to see black bears. They're just everywhere. So here's some views back in the 1930s. This is the workers for the Civilian Conservation Corps cutting trails and roads and campgrounds in Great Smoky Mountain National Park. The park itself straddles North Carolina, shown here in kind of the olive green, and Tennessee in the purple. The main road that goes across Great Smoky Mountains National Park begins near Cherokee, the town of Cherokee, and you wind up over the mountains and you take this beautiful drive on this 2-lane road. You get up to the top right at the state line between North Carolina and Tennessee, and that is called the Newfound Gap. Big parking lot here, beautiful place to stop. Then you make the slow descent down into Gatlinburg. Cades Cove is down here. You take the beautiful drive through Cades Cove from Gatlinburg. Neat little town. You can go on to Pigeon Forge and Dollywood. So nice park to visit in Dollywood. So here's the extent, the Great Smoky National Park, and then it kind of transitions into Shenandoah National Park. Here's just a little close-up view of the Great Smoky Mountain National Park itself without Shenandoah Park, which straddles North Carolina and Tennessee. I'm down here every summer. The last week in July, I go to a huge mineral show that's in Franklin, North Carolina, very close to Bryson City, and we usually take the drive across to Gatlinburg. So one of the highlights of Great Smoky Mountain National Park is Clingmans Dome. It's the highest point in the Great Smoky Mountain National Park. There's a side road when you get up to Newfound Gap. You take a side road that's about 4 or 5 miles long, and here's the parking lot and the walkway, and you're up there pretty high. You're about 6,600 feet above sea level. You can feel that altitude. You park your car, and then you take about a 1-mile walk, and you wind through the ridge here, and then they have this beautiful circular ramp, and you go up to the observation platform on Clingmans Dome. The rocks themselves, you get up on any place in the Great Smoky Mountains, all of the rocks there are extremely old. They date from 1 billion plus years to early Paleozoic and the Cambrian period. So like from 1 billion to 542 million years ago. Lots of metamorphic schists, phyllites, gneisses, some granites, lots and lots of metamorphic conglomerates in Great Smoky Mountain National Park. The Blue Ridge Mountains, the rocks were already there, but the formation of the Blue Ridge Mountains owe themselves to the collision that formed Pangea. It's about 280 million years ago when the continents came together. Great wedges of rock were thrust up from the basement of the continents, and these wedges of rock went on to become the very, very old rocks that formed back during the Precambrian. And these rocks resulted in the present-day Blue Ridge Mountains. So maybe it was Glacier National Park that was going to be covered. So our next national park is Glacier. Established as a national park in 1910, the Glacier National Park covers over 1 million acres. It's one of the highest visited parks in the United States. It averages over 3.5 million visitors per year. Naturalist and historian George Bird Grinnell, who has a glacier named after him, described the park as far away in northwestern Montana, hidden from view by clustering mountain peaks, lies in an unmapped corner. He called it the crown jewel of the continent. And it very, very, very much is. Glacier National Park kind of straddles the Canadian border. Of course, it's famous for the spectacular mountain ridges, the glacial features, and its glaciers. And probably one of the most famous highways and a thrilling highway to drive on is Route 2, which traverses the park, and it is going to the sun road. And there are various places to stop along here and overlooks. Glacier National Park itself consists of 2 mountain ranges, and I'm wondering if I have them listed on here. No, I don't think I have them listed on here. There is the Livingston Range and the Lewis Range in Glacier National Park. And if we look at a cross section through these mountains, these 2 spectacular mountain ranges, Glacier is famous for what we call the Lewis Overthrust, named after Lewis of the Lewis and Clark expedition that passed through this region. This gives you some idea of the forces within the crust of the earth that drive plate tectonics. We have this massive slice of younger rock that is of older rock. I'm sorry, I'm trying to move my little view here. We have this massive slice of older rock that has been thrust over Cretaceous rock. This massive overthrust, this fault line that's shown here in red. So the park itself consists of these mountain ranges that were formed through the process of weathering and erosion on this huge slab of rock that was thrust over other rocks as much as 50 miles to the east. And we know that this overthrust took place between 75 to 59 million years ago. In geology, Chief Mountain is a famous geologic location. It is an isolated block of rock that sits on younger Cretaceous formations, and it's been thrust over. It's actually part of this continuing layer down below here. So Glacier National Park is famous for its glaciers, its scenic beauty. Glaciers during the last ice age, during the Pleistocene, and still today, have carved these rocks. A little bit of glacial geology here. When glaciers move through a valley, the valley can transition from a V shape to a U shape. So we see this up at the Finger Lakes region in New York. So glaciers pass through a valley, and the erosion and the grinding of the rocks turn that valley from a V shape into a U shape. So here's a classic U-shaped glacial valley. Mountain glaciers that form on the side of a large mountain peak will wear back into the mountain and form what we call a cirque. A cirque is a bowl-shaped circular depression formed on the side of a mountain by a mountain glacier. And where you have 2 cirques on opposite sides of a mountain peak, the cirques will come together and they will form what's known as an arête. An arête is a sharp razor-like mountain peak or a ridge that separates 2 cirques. And you can see an arête there, and there's an arête here, and that's an arête, and these are little arêtes right there. So a little bit of glacial geology. Glacier National Park, back during the Pleistocene, resemble something like this little cartoon drawing. As the glaciers recede and melt away, we get all these glacial features. A sharp peak is a horn. Probably the most famous horn is the Matterhorn in Switzerland. Then we have cirques and tarns, these suspended lakes in the cirques, and a knife-edge ridge called an arête. A col, U-shaped valleys, hanging valleys where a river will flow through a U-shaped valley and plunge to another U-shaped valley down below. The recent NAGT meeting up in Ithaca, New York, Dagonic Falls on the shore of Seneca Lake is a hanging glacial valley. So in the mid 1800s, there were 150 active glaciers in Glacier National Park. That was in the mid 1800s. Today, there are only 25, and they are currently all in rapid retreat due to accelerated melting. We estimate, geologists estimate, that by 2030, all of the glaciers in Glacier National Park will be gone. So that's not long from now. That might be a little ambitious of a date. Hopefully things will turn around, but we're only, what, 7 years away from that. So that's kind of scary. So the loss of glacial ice, this is Grinnell Glacier. This is 1911. And I have to move my, let me move my little sidebar here of my, so here's 2016. So we're suffering this enormous loss of glacial ice, not just here in North America. Here's Sperry Glacier. This was Sperry Glacier in Glacier National Park in 1913. And this is what it looked like my box is covering that up over there. I can't move that now. So that's 2008. So without getting into the debate about global warming and what's causing the glacial ice to melt, we can see that there's a substantial difference. So Arches National Park, located in eastern Utah, became a national park in 1971. Covers 120 square miles. There were more than 2,000 natural open arches in Arches Park. It's a highly visited park in the American Southwest. It averages 1.8 million visitors a year. The park is so popular and there's limited access. So now, I'm not sure if this is still in place, but from April 1st through October 31st, I know the last time I checked, you have to make a pre-arrangement. They give you a timed entry when you can enter the park at one of the entrances, and then you need to leave by a certain time. Arches National Park in Utah, this is the Estrada Sandstone, which is Jurassic period in age, Mesozoic era, Jurassic period. This is an iron-stained massive sandstone that is up to 1,000 feet in thickness. So it's about middle Jurassic in age. It's below the Morrison Formation, which is famous for dinosaur fossils. So a little bit older than the Morrison in the Cretaceous, but this is a Jurassic age sandstone. How did these arches form? Well, this sandstone layer, the Entrada sandstone, was deposited during the Jurassic period between 180 to 140 million years ago. There was and still is below this layer of sandstone. There is a massive layer of salt, and the overlying weight of the rock causes the subsurface layer of salt to shift and move, and that caused the overlying Entrada sandstone to fracture and crack. And then as a result of these open fractures, groundwater was able to penetrate, slowly weather and erode the rock, creating a series of deep canyons and ridges. Some of the ridges, the weaker areas, then collapsed, forming these arches. And this is pretty much how the other arches in the American Southwest formed. So Arches Park is famous for, this is the 52-foot tall delicate arch during the day and at sunset. And this is what the Arches Park looked like. And Utah, this region of Utah back during the Jurassic period. So I wanted to include a little bit of this. Back during the Jurassic period, we see the rapid rise of the large theropods and the large sauropod dinosaurs. So Utah is a prime hunting ground for dinosaurs. As a matter of fact, Allosaurus, which means different lizard, Allosaurus was discovered at the Cleveland Lloyd Quarry in Utah. And the Cleveland Lloyd Quarry in Utah is still a very important paleontological dinosaur site today. And it is famous for the numerous skeletons of Allosaurus that have been discovered there. And they're still removing Allosaurus fossils from the Cleveland Lloyd Quarry. Allosaurus was a large theropod that it predates T-Rex by over, oh my goodness, probably close to 100 million years. So how are we doing on time, Jerry? Are we okay? 8:11?
You give me 10 more minutes.
10 more minutes. I'm good. Okay, so we'll go through. Okay, so here's Isle Royale National Park. Isle Royale National Park is in Lake Superior, Michigan. Isle Royale, a beautiful, beautiful park in Lake Superior. It was established as a national park in 1940, and it is also a UNESCO, a United Nations Educational, Scientific, and Cultural Organization International Biosphere Reserve, and it was designated as such in 1980. So if you go, I was up in Michigan last June, finally made it to the Upper Peninsula of Michigan, and Meryl and I spent 8 days, which was not nearly enough time, from St. Ignace to Sault Ste. Marie to Munising and Ishpeming and the famous iron and copper ranges of the Keweenaw Peninsula. We did not get to Isle Royale, so I can't speak about this in person, but Isle Royale is actually the same type of rock system that makes up the Keweenaw Peninsula, the famous copper-bearing rocks of the Keweenaw and the mining region that sticks out into Lake Superior. So 1.1 billion years ago, just prior to the Grenville orogeny, the North American continent, Laurentia, was undergoing a rifting. And this was called the Great Mid-Continent Rift. It was during the Precambrian. The rift began in the vicinity of modern-day Lake Erie and extended up through the Great Lakes and down into the Midwest. So our North American continent was splitting apart. But what we believe happened is then the continents came together during the Grenville orogeny and closed up this rift. So this mid-continent rift is now buried under thousands and thousands of feet of newer sediment. But when this rift was opening, vast amounts of basaltic lava were filling this great valley system in the ancient North American continent. So as the rift widened, plumes of magma were rising and filling the rift, and then intermittent lakes and interior continental oceans interspersed with the lava and laid down layers of sediment. So we had layers of sediment, layers of lava. The rift itself failed, and we had something like this form. So this is back during the Precambrian. 1.1 billion years ago, over 10,000 feet of lava filled this rift. After the lava formed, hydrothermal fluids filled the vesicular basalt with copper, native copper. And these layers of basalt are what's known as the Portage Lake volcanics. In present day Keweenaw, this is what it looks like. So when you go to Lake Superior, this is the mainland of Michigan. This would be the Keweenaw Peninsula. And then you travel across Lake Superior, and Isle Royale is actually a little point, a little island of basaltic rock that sticks up. It's part of the syncline that extends down through Lake Superior. And the Great Lakes themselves, though not carved out entirely by the glaciers, but the glaciers came down during the last ice age, the Pleistocene, and helped form the basins that the lakes now occupy. So here's what we're looking at, a cross section. Let me just go back to the map here. So here's Isle Royale. So a cross section from Isle Royale across this part of Lake Superior to the Keweenaw Peninsula looks like this. So here is Isle Royale. The dark green here, these are interbedded volcanic rocks and sedimentary rocks that date back 1.1 billion years. Then we have Lake Superior sitting on top of it. Each side is bounded by a fault. The floor of Lake Superior is now filled with sedimentary rocks, but these layers of basalt are absolutely packed with mineralized deposits of copper. And this was one of the largest copper producing region on the Earth. So if we just look at Isle Royal, the rock layers, these are all layers of basalt intermixed with some metasedimentary rocks. They're all copper bearing. So another way to look at that is here's Lake Superior and the Keweenaw Peninsula, and these Portage Lake volcanics that date back 1.1 billion years are rich in copper. And when I was up there, every rock that you pick up from the Keweenaw Peninsula and the UP of Michigan, we find these beautiful amygdaloidal basalts. Amygdaloidal means that the basalt is vesicular. It has gas bubble pockets in it, but the vesicles are mineralized from the hot hydrothermal waters. And this is a piece of vesicular basalt that I picked up on the Keweenaw, cut it in half and started to polish it. This is calcite, feldspar, jasper quartz, prehnite, copper. There's chrysocolla, azurite, malachite. There's tons of different minerals found in these amygdaloidal basalts, but the most important one is this. So these are samples of rock that I collected on the Keweenaw Peninsula, which are the same rocks as Isle Royal. These are samples of basalt that I brought back with me and cut and polished, and that is native copper that is 1.1 billion years old from the Keweenaw Peninsula. Large pieces of copper. I brought my metal detector up there with me, and no matter where you walk, the metal detector pings. This is the Copper Harbor conglomerate. This is an ancient conglomerate that filled this giant rift, and then the conglomerate itself was metamorphosed and also contains copper, and you can start to pick out some of the little tiny bits of copper in here. It makes a beautiful rock when it's cut and polished. So let me see where else we go. Here's what I'm going to finish up with. This is my last national park, Hawaii. At least I think it is. So I'll go fast, Jerry. I'll finish. So Hawaii, Hawaiian Volcanoes National Park was established in 1916. It's on the Big Island of Hawaii. It contains Kilauea and Mauna which came back to life last year. Like Yellowstone, Hawaii sits over a mid-plate tectonic hotspot, a plume of magma. And that plume of magma, it's one of the largest, most active volcanoes in the world. In 2018, just before we went there, this large volcanic eruption took place in what's known as the East Rift Zone, which would be right here. So this was the volcanic eruption in 2018. This happened very quickly. The ground split open, the lava started to pour out, and I want you to remember this intersection right here. See that intersection of these two roads, this spot right here. So the lava is coming towards you, and I'm going to jump down here, and let me see. I have a photograph of us standing there. I've just got to find it. There it is. All right. So we were there, the lava flows, we were there in March of 2022 with our geology students, and there's the solidified lava. So we drove up that road, and here's the solidified lava, which is, you're looking right there. You're looking up what used to be a road. So that's as far as we could drive. We climbed up on top of this lava flow. It was still smoking and steaming, but there was no active lava. And here's a close-up of that lava flow up on top. And that's my department chair, and these are some of our geology students. So in 2022, the next volcano to the north, Mauna Loa, was just temporarily inactive. Geologists on Hawaii began to pick up some rumbling, and they knew that magma was rising towards the surface. And this is an enhanced satellite photograph. So this was the first eruption of Mauna Loa since 1984. So here's Kilauea, the active volcano. And in 2022, Mauna Loa came alive and produced some large, spectacular lava flows that flowed to the southeast and to the north. Mauna Kea is now, we believe, completely inactive, and that's where the large observatory is. So we were there with our geology students in March of 2022. This is Kilauea. That is the large caldera on the active volcano on the southern shore. So there I am. And these are our geology students. Where this picture was taken, we're looking down into the caldera. There was an active eruption taking place. Here's on the slope of Kilauea. This was a United States Geological Survey volcanologist that gave us a really, really nice talk about the volcano. These are our students, and that's my department chair at Pitt Johnstown, Dr. Kerrigan. So you can hike to the volcano at night. There is a road that is closed because it's cracked and broken because of the volcanic eruption. They call it Devastation Point. So you park your car and you walk 1 mile and you go at night and you stand at the top of the crater. And that is what Kilauea was doing when we were there in March of 2022. So this is when we first arrived, just before it got dark. And after it gets dark, you can see the lava plumes. These plumes of lava down here are about 400 or 500 feet in height. So that gives you an idea of the size of this caldera complex. And then, of course, we took a selfie. That's myself and my wife with the active lava flow in the background. And then, of course, you have to do all the touristy things. This is the famous green sand beach, which consists of green olivine crystals. This is on the southern shore of Hawaii National Park. So these are volcanic ash layers. And this was one of the most spectacular things I've ever seen. Everything that's green in these photographs, and I should have had something here for scale, but this looks like green algae, but those are green olivine crystals, peridot. And the vesicular basalts in this area of Hawaii are just completely filled with crystallized olivine. So you get the red volcanic sand. The white is the coral, natural white coral sand. So you get the green olivine, the white coral sand, and the red volcanic sand with the black basalt. And here's a group picture. This is the green sand beach on the southern shore of Hawaii within the park. You can hike to this. It's about a 3 or 4 mile hike, but we paid one of the locals and we all loaded into the back of his pickup truck and he drove us here. He had a huge pickup truck and he drove us here and then waited for us. So we went swimming and I didn't collect a single thing from Hawaii. You're not supposed to collect any rocks because Pele does not look favorably on that. And then probably one of the highlights of our trip is this is Kilauea Iki. Little Kilauea erupted in 1959. And the big volcano is just on the other side of this ridge in the background. You take a 4 mile hike, you walk through these cliffs in the background, and then you climb down the crater wall and you walk across the caldera floor from the 1959 eruption. And this is on the crater floor. These are our geology students. There is a trail that you follow, but you can walk really anywhere you want. And this is the volcanic vent. This is where the lava came out back in 1959. And you're walking on the solidified surface of lava. There were test boreholes here that they've drilled down to make sure that the surface is stable. But it's still, there was still places where steam was coming up. And it's kind of a little unsettling to know that you have a huge magma chamber that extends down into the mantle down below you. So there we go. There's our first set of national parks. So hopefully you enjoyed that. I'm going to stop screen sharing. And not bad, 8:24. If there are any questions, I'd be happy to take them. I know I went kind of fast, but I realized I couldn't do all 63 national parks tonight unless I just showed one slide of each national park. So, and even then, it didn't stretch. So,
by the way, the 2022 attendance at Smoky Park was 12.9 million.
What was it? 12.9.
Yeah, 12.9 million.
That's impressive.
Yep.
Yeah, that's impressive. So, right. So there won't be a test. There's no test on this. So we can always do a national parks part 2. So yeah, I'm down. We go down to Great Smoky Mountain National Park every the last week in July because there's a huge mineral show down there. And then we usually take the drive across the main highway up to Newfound Gap, go to Clingmans Dome, and then down into Gatlinburg. And then the last time when we were there 2 or 3 years ago, we went over to Pigeon Forge in Dollywood, which was spent a day in Dollywood, which was pretty neat, or an amusement park. So, but it was nice. So, thank you very much.
All right.
It's nice
Anybody,
to be
anybody have
back
any,
with the group again? So,
anybody have
Yes,
any questions?
I do.
Yeah.
If Congress makes the national parks, then can somebody, some president just decide that they're not a national park anymore and open them up to development and exploitation?
No, that's I don't believe so. That is not within the powers within the Constitution that's designated to the president. So the president can designate a national monument. Like if President Biden wanted to make Johnstown, Pennsylvania a national monument, he could do so by presidential decree, and it would stay a national monument. Then he could recommend to Congress that it should be a national park, but then the full Congress, the Senate and the House must act to vote that in to be a national park. And there's a difference in the type of protection it has and the money that it's given to preserve it. So, but I don't believe I would check on that, but I am pretty positive that a president does not, the powers that are provided to the president, he cannot remove a national park from national park status. The interesting question is, I don't know if Congress can. So there's an interesting question, and I don't know the answer to that. Like, suppose Congress wanted to remove Yellowstone as a national park because they discovered vast amounts of gold within the park. And they were lobbied to mine that gold because it would bring billions of dollars to the national economy. So there, I mean, I'm just saying that hypothetically. So that's something I'd have to look up. I don't know the answer to that. Dan posted the question: how are the ages of the multiple older calderas leading to the current one in Yellowstone dated? Yeah, uranium to lead, radiometric dating. So we can very accurately. We don't use carbon-14. Carbon-14 is like for organic remains. It's good till about 55,000, 60,000 years, stretching it. But we use the radioactive isotopes, uranium to lead, rubidium to strontium. It's mainly uranium to lead. And any one of us could do that. You could collect a sample of rock and send it to, I know New Mexico State University does a lot of that geochemical testing for other universities. You can send a sample off and pay the fee, and they'll give you a radiometric date on it using uranium to lead. So that's how we date the, especially igneous rocks, because they always have a small amount of uranium in them. So.
Okay. Great program, and there will be a number 2 section coming about.
Yeah, we could do a number 2. We could do a second national park, and maybe sometime in November, December. Sure, if you need an evening. In my opinion, which national park is the most interesting geologically? Oh boy, that's a good question. I don't know. I tend to like Jerry said, I like structural geology. So Glacier with the Lewis overthrust. Glacier. I also think Yellowstone to volcanologists, but I think also the Petrified Forest, because I think the history of the Petrified Forest, and I know that I read several papers, and I'll have to try to find them, and I'll send them to Jerry, that the general consensus is that those logs were possibly transported in from hundreds of miles away on large east to west flowing rivers back during the Triassic, during times of flooding. So, yeah, I like Glacier. So.
And the national parks are like everybody in this room. Everybody has their own characteristics, and
right.
The national park has its own geological characteristics, and
Right, right. And I think
Makes everyone special.
yeah, yeah. And there's a lot of neat little, facts and trivia like what is it? Trying to think, there's a lot of states that have no national parks. There tend to be more national parks out west. Trying to think, what is the most northern national park? Might be Acadia in Maine, I think is the northernmost national park,
Right.
at least in the 48 states.
Right.
Yeah. So
Okay, before we leave, during the program, I learned that we have a regular member who's visiting with us tonight from this spot right here. And Gail Crow, if you want to unmute yourself and tell us where you're listening in and watching tonight from.
Yes, Jerry. We are off the coast right now of Greenland. We're on a ship, and we're out to sea, and we'll be hitting Iceland in about 2 days. And no, I cannot bring any basalt home in my suitcase.
Darn. All right. So you're actually on a ship.
Yes, we're aboard ship right now.
Wow. You're roughly 1,900 miles from me right now, from what I could tell. So
Nice. Way to go. That's great.
you might be the furthest transported Zoom member viewing. So we'll give you that trophy when you get home.
that's pretty awesome. Did you land in Greenland? Did you land on Greenland?
Yes, yes, we were out. We were on the shore today. We were in it's hard to pronounce Qaqortoq, Greenland, and now tomorrow we're going to go to Nanortalik, Greenland.
Okay. Wow.
That's neat.
Will you be able to do?
Nice.
Will you be able to do a program for us when you get back?
Well, I could try. Yeah.
All right.
That'd be good.
Great.
Yeah, some of the oldest rocks found on the Earth are Greenland, right, Jerry?
That's right.
Really old Precambrian, yeah, and some really unique minerals too.
Yeah, I'll choose that rock over the basalt from Iceland. So if you can get a 3 billion year old rock from Greenland, just put that in your suitcase.
Okay, well, I did pick up a stone this morning from the shore. It looked like granite to me, but I'll be bringing that one home. It's a little one.
Okay. Well, great to have you. Thanks for your dedication, and tell everybody on board tonight that you were watching the Zoom Rock Room. Okay.
Thanks, Mary.
Thanks, Gail. Enjoy the rest of your trip.
Thank you.
Okay, that's going to be it, folks. Thanks for the great program, Mr. Steve, and thank Mel for getting that picture inserted there in the last minute. I can't do anything because I'm locked into the recording here, so that's why you have a co-host to find things like that. So that's right. So we'll see everybody back here in 2 weeks.
Sounds
and
good.
have a good those 2 weeks, and stay cool at least for another 5 days. Okay. We'll see ya.
Thanks, Jerry.
Bye.
Thanks, everyone. Bye-bye.
Bye. Thanks for the program.
You're welcome. Bye-bye.
Bye.